Alright, so in this video, we're going to go over some of the most important math and physics concepts that you might need to know for ES 123 fluid mechanics this semester. Just remember that a lot of this stuff may be new, and the derivations you're not expected to know. Just try to understand them and understand how to use them. Alright, so the first important concept to remember are the dot and cross products. So first, the dot product. Mathematically, we can calculate the dot product by taking the pairwise products of each of the components of the two vectors and adding them up. So if you have x1, x2, x3, y1, y2, y3, the dot product is simply x1, y1 plus x2, y2 plus x3, y3. Now, from a more intuitive perspective, the way we can understand the dot product is essentially we're taking the projection of one vector onto the other vector multiplied by that second vector. So we take the projection of x onto y multiplied by y, and that is the way that we can understand the dot product physically. So if we take in a specific case, as we see here, where the two vectors that we're taking the dot product of are perpendicular to each other, then we have the special case that x dot y, in this case, would be equal to 0. So we just remember that if two vectors are perpendicular, their dot product is 0. Another important but less intuitive concept is the cross product. The formula is shown here, but what's most important to remember is that if you have two vectors in 3D space, the cross product is going to be the vector that's perpendicular to both of these vectors, so it's perpendicular to the plane containing these two vectors, and it's going to increase as the angle between these two vectors gets closer and closer to 90 degrees. And if these two vectors are on the same plane, then the cross product between them is going to be 0. Now let's look at divergence, gradient, and curl. We can see here all these operators defined in three different coordinate systems: Cartesian, cylindrical, and spherical. Cartesian and cylindrical coordinates are going to be the most important for fluid mechanics, so let's look at how they're defined. As you should already know, Cartesian coordinates is simply defining every point as having an x, y, or z coordinate, as we see here. And cylindrical coordinates defines every point as having a certain angle, which is a certain phi from the vertical, a certain rho, which is, defining the radius of the circle, and then the z, which gives the depth into the plane. So now let's look at the gradient in each of these coordinate systems. So the way we define gradient in Cartesian coordinates is simply by taking the partial derivative of the scalar function in the x, y, and z axes. So we can see that the definition of this in terms of the physical intuition is that if we have a certain point at any point in our space, the gradient is defined as the rate of change of the scalar function in all three axes, which also actually happens to correspond with the direction of greatest increase of the function. So we can see that at any point, this is what the gradient will look like in Cartesian. This same physical intuition applies for the other coordinate systems, but the mathematical definition is a little bit different. Cylindrical coordinates, for instance, you can see that it's pretty similar to just taking the rate of the partial derivative of the function with respect to rho, phi, and z, except we have a little bit of a different term here with 1 over rho. So just keep that in mind when you're doing your calculations. All right, now let's talk about divergence. While gradient was defined for scalars, divergence is defined for vector fields. So suppose we have a vector field in this box region that is appearing to point outward. So the vectors are kind of exploding away from the central point. Then we say that in this region, the divergence, which is denoted by this del dot, the vector field, is positive. Conversely, if it appears that the vectors are kind of imploding, they're pointing towards this point, then we say that the divergence of f is less than 0. So divergence quantifies the extent to which this vector field is expanding away from this point. And we can see the definition of a divergence up here in this table. Basically, we take the partial derivatives of our vector in each of the directions, and then we sum them up in Cartesian coordinates, and we have a similar kind of function here for cylindrical coordinates. Now, as denoted here on the side, it's important to remember that, as I said before, the gradient takes us from a scalar function to a vector function, whereas the divergence takes in a vector function and spits out a scalar function at every point. All right, so now let's look at curl. As the name suggests, curl basically tells us how much a certain vector field is curling in a certain region. So let's look at this point here. We can see that the vectors are kind of rotating around this point. And so we can then say that the curl would be pointing kind of in this direction, and it would have a magnitude that's associated with kind of how much and to what extent the vectors around it are curling. We can kind of think about it as a line integral zoomed in onto this point, because we're kind of saying how much these vectors are curling around that point. Now, in contrast, if we look at this point, we see that there's no net curl in that area because, we have some vectors that are curling away in both directions. Now, mathematically, the curl is defined in Cartesian and cylindrical coordinates by this cross product here, but I would suggest not worrying about that right now. If you ever need it, you can look it up online. The important thing to remember is that the curl takes in a vector field and spits out a vector field. So it's worth remembering, to distinguish between gradient, divergence, and curl, what it takes in and what it spits out. Okay, so now that we've defined gradient, divergence, and curl, let's look at some crucial relationships between them. So the first thing to remember is that the curl of the gradient of a function is always going to be equal to the zero vector. Now you can prove this mathematically, but one way we can understand this physically is that let's say we did have a function that had a gradient that kind of looked like this. So this is what the gradient of our function f looks like. Then what that would essentially mean is that if we were to follow the path around here, right, which should theoretically be the path of greatest increase of the function, we'd be increasing everywhere along this path, and we would end up back at this point, and it would be greater than we initially started. So we can't have a function that has multiple definitions at a given point. So this tells us that at every point in space, the curl of the gradient has to be zero. Now, the second important relationship to remember is that the divergence of the curl of a vector is always equal to zero. Now, this is a little bit harder to intuitively understand, but I would just say that in a certain region, if you take the circulation of a certain vector field in a certain region, that has to stay on the surface. It can't diverge. All right, so now let's look at an important application of gradient and curl, which is known as Stoke's theorem. So we can see here that if we have any surface and it has a boundary here that we call C, so we see that here this boundary is this little circle here, then if we take the line integral of our function around that boundary, that must be the same thing as taking the surface integral of the curl across this whole surface. Now, the way that we can understand this is that if we're taking these little circulations, right, and we're adding them up across everywhere in the surface, all of these circulations are going to kind of cancel within each other, except for the circulation which is around the outside. So that's how we derive Stoke's theorem from an intuitive perspective. Okay, so similar to Stoke's theorem, we have Divergence theorem for divergence, which basically says that if we have a certain volume, then the volume integral of the divergence at every point within this volume has to add up to the net flux integral of the vector function at the surface. So kind of as I was saying before, since the divergence is kind of telling us how much explosiveness, how much of the vector is entering or leaving every point in this space. If we add up the divergence everywhere, that should basically tell us what the net flux of our vector field is through the outer surface. All right, so now I'm going to go into some operators that you might not have seen before, but are going to be super important for fluid mechanics. And the first is a Laplacian operator. And we can see here that the Laplacian operator is simply defined as del squared of phi, which is how it's written, is basically just the divergence of the gradient of a scalar function. And so mathematically, we can see that we're just first applying the gradient and then applying the divergence, and we get these formulas. But more importantly, let's try to understand this intuitively. Basically, the Laplacian tells us the degree of concavity, or how much of a peak we are at a given point. So let's look at this big peak here. Turns out that the Laplacian at a peak is negative, because if we look at all the neighboring points, the gradients are kind of pointing in towards this point. And so if you were to now think about those gradients and then take the divergence of those, well, then you would have a net influx of gradients. And so then this would tell us that the Laplacian would be negative because we have things that are flowing into this region. Now, on the other hand, if you look at a trough like the one that we see here, right, we can see that in all directions, we're kind of pointing up. So that's what our gradient looks like. So then if we were to, think about the divergence of the gradients, then the Laplacian would be positive. And so this is kind of similar to thinking about the double derivative, right? This is kind of a concave up shape, which is a positive Laplacian, and this is kind of a concave down shape, which is a negative Laplacian. So that's kind of how you think about Laplacian. All right, another really important concept to understand is the material derivative. Basically, it asks the question, if we're moving along with a particle in space in a vector field, what is the rate of change that we experience as we move along with the particle? This is actually very similar to a concept that you may have learned in regular multivariable calculus, which is the chain rule. And in that context, we may have asked the question, if you have a scalar function, like temperature as a function of x, y, z, and you're moving along with the particle, what is the rate of change of the temperature with respect to time from the perspective of that particle? Well, what you do is you say, in what direction am I moving? What is my velocity vector? And I dot that with the rate of change of the temperature with respect to x, y, and z. And this basically tells me, in the direction that I'm moving, how much is my temperature changing? So this might be a pretty intuitive concept for a scalar function. But now let's apply this to a vector field. Suppose we have a vector field A, which is defined as having three components, ax, ay, and az. We can now basically apply this same chain rule to each of the components of this vector field. So we're going to say d a sub x dt is equal to velocity vector dotted with the gradient of a sub x. And we can say the same thing for a sub y, and we can say the same thing for a sub z. So now we can essentially just shorten this into a simpler notation. What we're going to say is dA vector dt is going to be equal to the velocity, the direction that we're moving in, dotted with the gradient of vector A. Now, if we go back to what I was talking about before, I mentioned that the gradient is usually applied only to scalar functions. But in this case, we're just going to define the gradient of a vector as the vector that incorporates, that consists of the gradient of each of its components. So the gradient of ax, the gradient of ay, and the gradient of az. And we can see how mathematically, if we dot that with the velocity vector, we just essentially get these equations that we made up here. So this is a form that we'll very often see. And just remember that this form is assuming that the A vector field doesn't actually change inherently with time. But if we wanted to incorporate that, we can also add this del A, del T, and this would be accurate for a field that is also changing with time and we're moving through it. And just to recap, I know this is a lot of math, all that we're saying here is that if we're moving through space along with the particle, then this is the derivative that is experienced, the derivative of the vector field that is experienced as we move through space. All right, now I'm going to go over ordinary differential equations, which are basically the standard single differential equations that you would have studied in regular calculus. So let's imagine we have a particle that's traveling through a fluid, and it experiences this equation for velocity, such that its change in velocity is proportional to negative k times velocity. The standard way that you're going to want to solve these kinds of equations is to separate the variables. So you may have remembered separating differential equations. What we do here is we divide the negative kv onto the left side. So we have 1 over kv dv is going to be equal to dt. And then we integrate both sides. And we get negative ln of kv over k is equal to t, and then remember we have plus some constant. So remember, all we've done here is just separate variables and integrate both sides. So now let's figure out what this c is. Suppose we have the case where v at time 0 is equal to some constant that we call v naught. Well then, if we plug that into this equation, apply this initial conditions, then what we're going to say is that negative ln of k v naught over k is equal to 0 plus c, which is going to be c. So we've essentially solved for c here. this constant, which is the integration constant. And so now when we plug back in, we get the overall equation negative ln of kv over k is equal to t minus ln of k v naught over k. And we can now just, shuffle around some variables and solve for v as a function of t. But I just wanted to make sure that we have a general idea of how you separate variables in a differential equation and you apply the initial conditions to eventually solve for the function. All right, now that we've reviewed a bunch of math, let's look at some physics concepts. This is going to be a much shorter section. First, let's examine Newton's second law. We usually say F equals ma, but let's be more specific. The sum of forces on a particle, on an object, is equal to the rate of change of mass times the velocity vector. Just to be clear, we're writing it like this because it's possible for mass to change and velocity to change in a certain context. But it's also important to remember that this applies only to a specific particle, and we have to be moving along with the particle. This is going to be super important for fluid mechanics because we're going to have a lot of particles in a system, and we have to remember that when we apply Newton's law, we have to be tracking a particle that has a specific mass, and that's important to remember. All right, so just to take an example of this, let's say we have a ball sliding down a hill. We have friction applying a force in this direction. We have gravity applying a force in this direction, whatever, mg sine theta in this direction, force of friction in that direction. And you would be saying that in the direction of mg sine theta minus the force of friction has to be equal to ma. So this is just a classic example that we would have done in regular introductory physics. And this is going to become much more complicated when we're discussing fluids, but it's good to just remember our fundamentals. The second important concept to remember is conservation of energy. So if we have a ball that we throw up into the air with a certain velocity, 1/2 mv squared is its initial energy. It reaches some maximum height, at which point it doesn't have any kinetic energy and it only has potential energy, which is mgh, and we can express the relation that mgh is equal to 1/2 mv squared because of the assumption of conservation of energy, which is that the energy 1 plus the work done on an object, the sum of the energy 1 is equal to the energy final of the object. Very simple fact, but let's just remember that. Also remembering that if we have cases with friction, then we cannot just set the initial and final energies equal to each other because there will be external work done in the system. So just remember when external work is being done or when it's not. All right, so the last concept that we're going to talk about here is pressure and shear, very briefly. We're going to go into much more detail in this during the course, but let's first remind ourselves the definition of pressure. If we have an object, be it a fluid or a solid, the definition of the pressure exerted on this object is the force divided by the area. So pressure is equal to force divided by area. Now, a related concept, which actually has the same units, is shear. And shear basically tells us if we have two sheets of fluid and they're moving at different velocities. Let's say this one is moving in this direction and this one is moving in this direction. What is the force experienced at the boundary between these two sheets? And that's the shear force. And that's also actually expressed as in the units of force over area, but we're going to go into much greater detail into how you calculate that and how you use that. But I just wanted to give you a brief overview of some important forces that are going to be relevant for fluids.